And so my talk is about models of spontaneous wave function collapse. I will give a general introduction, an update, and also the connection to this workshop with the mind and agency. So let me start. I hope you can. Okay, I hope you can see the slides changing. So the motivations underline models of spontaneous wave function collapse, which goes into the superposition principle, the problem with the superposition principle, the problems of the foundations of quantum mechanics, the measurement problems, basically. So what is the situation? Situation, just, I mean, most of you probably know, but just as a warm-up, you know that the quantum mechanics is rooted in the superposition principle. So the possibility to superimpose states of a physical systems, like in the picture here, atom here plus atom there. And then the question already arises, what does it mean for a system, for a massive system to be in a quantum superposition? I mean, it's an interesting question, but I will dismiss it for the time being, let's say. But still, I mean, in a way or another, superpositions at the microscopic scale have been tested experimentally in a variety of ways. But then the measurement problem comes, the problem of quantum mechanics, that also macroscopic systems should be in a superposition, first of all, because they're made of atoms, which are quantum, and also because the linearity of the theory doesn't have, at least theoretically, a limit of validity. Superposition should occur for every physical system. And in particular, they should float the macroscopic domain. As soon as a microsystem interacts with a macro object, the superposition should reach also the macroscopic scale. And that's the essence basically of the argument brought by Schrödinger with the cat paradox, that the cat in the box should be in a superposition of being dead or alive, at least until someone opens the box and sees what's going on inside. And that's, I mean, that's kind of at least an embarrassing situation and the source of problems in the definition of the theory. So what is the standard prescription in quantum theory? The standard prescription is that there is a divide in some way between the quantum world, or that's the orthodox formulation. There is a quantum world and there is a classical world. There is a quantum world of which includes the physical system that one wants to study quantum mechanically, but there is also a classical world of measurements and observers. And observers decide what a measurement is and how it acts on the physical system. And then at the end of the measurement process, the wave function collapses with the Born rule. This is the usual way of presenting quantum mechanics, which is a very effective, which works excellently, or even more than that from the practical point of view. But again, the problem is still there. And here I use, I mean, among the many quotations one could pick, I picked one of Steven Weinberg. So the Copenhagen interpretation assumes this mysterious division between a microscopic world governed by quantum mechanics and the macroscopic world of apparatus and observers that obeys classical physics. And the point is that this division is not well defined. It's an arbitrary, it's subject to interpretation, but lies in the definition of the theory. So the theory is not well defined, and then one seeks for the different theory or different interpretation of different something in order to make our understanding of the quantum world more precise. So there are many options, of course. There is the pilot wave theory or Bohm mechanics, the way you want to call it. There are many words. There are several other options. And the one I want to present here are models of spontaneous wave function collapse, which basically the name tells what's going on. So the idea behind these models is that there is no sharp division and arbitrary division between a microscopic world and a macroscopic world, but there is a continuous transition from a quantum world to a classical world. And how do you move from a wavy world where things are diffused in space to a world where things are well defined and objects are localized in space via a nonlinear equation? That's the typical way of doing these things in physics. You have a nonlinear equation. So in these models, you have nonlinear and stochastic modifications of the Schrödinger equation in such a way that in the microscopic domain, nothing more or less changes. You still have the usual quantum dynamics. And then when you move from the micro to the macro world, these nonlinear and stochastic terms become more and more important, more and more relevant, and make sure that the wave function is always localized in space. So it's also interesting to see how two different ways of describing nature, a wavy nature and a particle-like nature, can be contained within the same mathematical formalism. And of course, in particular, in these models, you have a clear description of a measurement process. A measurement process is something big that interacts with something small. The interaction is governed by this modified equation. You can solve the equation. And the final solution, unsurprisingly, is that at the end of the measurement process, the outcome is well defined, is distributed with the Born rule, and as a byproduct, the wave function of the microscopic system is changes according to the von Neumann collapse process. So all these rules, which are postulated by quantum theory, can be derived by solving the dynamics of these models. This is one of the nice features of collapse models. And there you have the reference to the first consistent model, the GRW model by Gherardi and collaborators of 1986. So just to show an equation, then my talk will be kind of easygoing, but just to show an equation which grounds mathematically these models. Here you have the typical equation for the equation for the CSL model, the continuous spontaneous localization model, and other similar models. You can see that it's an equation for the wave function, because we want to talk about the collapse of the wave function. So it doesn't help to work at the density matrix level. You have to work with the wave function. And it's a stochastic equation because you have the noise, W of t. It's written in the Ito form, but for those of you that are not familiar with Ito calculus, you just divide by dt and you have an ordinary equation. It's a random equation with a noise. It's a nonlinear equation. You see that the quantum expectation of the operator m appears in the equation. So the wave function enters 3 times into the equation. So it's a nonlinear equation. And what else? The blue part is the usual quantum dynamics. So the structure of matter, so to say, it's embodied there. And the red part, it's the collapse of the wave function. That tells you that a macroscopic object, for example, is quantum mechanically in its constituents, in its internal structure, but as a whole behaves classically because the center of mass cannot spread out in space more than a very small quantity. What else? So H is the Hamiltonian, I said. W of t is a noise, which is white in time. It's not necessary, but makes the calculations much simpler. And it has a correlation function over space. So it's a field over space and time, white in time, and correlated over space. And G is the correlation function. M is the mass density operator written in a non-relativistic regime. You could also put there the mass density of a fermionic field or a bosonic field, a relativistic fermionic field like the Dirac field that doesn't cause any specific problem. Here it's at the non-relativistic level. So M is the mass of the particle, A daga A are the creation annihilation operator, usual formalism. But for the practical point of view, the way you want to think of that is that this is a position operator. So it's like a position localization that makes the wave function localized in space. The rest are just mathematical technicalities. This general equation includes in particular 2 important models which have been discussed in the literature. The first is the one I mentioned before, the CSL model, continuous spontaneous localization, first proposed by Pearl and also by Gherardi and collaborators between 1989 and 1990. And basically you see that what characterizes the model is the correlation function, which has a Gaussian profile with a width RC. Is the width of this Gaussian, which basically RC measures. So it's the correlator in space of the noise, and basically that sets the difference between a microscopic superposition, which is left unchanged by the dynamics, and the macroscopic superposition, which is in space, which is localized in space. So if you have a superposition, which is mathematically speaking a superposition, but very tiny within RC, so it's like 1 femtometer here plus 1 femtometer there. So technically speaking, mathematically speaking, this is a superposition. But from the physical point of view, it's a localized state because it's too small. But if you have 1 meter here, 1 meter there, the 2 states of the superposition, then that's a large superposition and it's collapsed by the noise. So RC sets the threshold between a micro world, a micro distance and the macro distance where quantum and classically respectively occur. Lambda sets the strength of the noise. The stronger lambda, the faster the collapse of the wave function. The other option is the DP model, the Dioschi-Penrose model. We'll say something about that. The correlation function has a Coulomb form, 1 over R, where with the only natural constants. Capital G is the gravitational constants. Of course, H bar is H bar. Okay, so this is just an overview of the mathematical setting. What is the physical content of these equations? And I already presented that, so I'm just summarizing that. These are the typical cases which have been considered in the literature. So if you have a microscopic superposition, like atom here plus atom there, an electron here plus an electron there, basically nothing changes. The mass of the system is too small. And so these nonlinear terms are there, but they are very weak, and you can neglect them for all practical purposes. The wave function superimposes, diffuses, it moves, it jiggles a little bit, but it diffuses over the space. And quantum mechanically, so the usual quantum behavior modulo tiny modifications. These tiny modifications actually are important from the experimental point of view, but still they do not prevent the quantum behavior of microscopic system to build up. But when you have instead a macroscopic object like the Schrödinger cat here plus there, in the picture you have many atoms here plus many atoms there, then you have an amplification mechanism which is built into the dynamics of the system. Now the collapse of the wave function is, so to say, n times, that depends, I mean, the model, but morally, let's say, n times faster. So if for a single atom, the collapse is very slow, very weak and negligible for all practical purposes, for a macroscopic object, it becomes very fast, because a macroscopic object is made of 10 to the 23, whatever, atoms or nucleons. So it's 23 orders of magnitude stronger, and something weak multiplied by 10 to the 23 can become something very strong and very fast. And this is how these models, is precisely for this reason that these models can combine both the quantum behavior of microscopic system and the classical behavior of macroscopic objects. Nevertheless, not all macroscopic states, not all complex quantum states are localized in space, because take the third box, where you have many atoms. So you can have also a gas, a classical gas, a macroscopic number of atoms, but they are not all the atoms here plus all the atoms there, or the gas here plus the gas there, but individually, each single atom is in a superposition, which is what happens, for example, in cold atoms experiments with BC, this kind of thing. It's a single atom superposition. So you have many atoms, but separately in a superposition. And again, we fall into the case of the first box. The superposition, the breakdown of the superposition principle is there mathematically, but it's very weak and almost negligible in all practical situations. So you have to have a specific type of superposition in order to trigger the collapse of the wave function. What happens to other degrees of freedom? I spoke only of position. What happens to momentum? What happens to spin? What happens to energy? Well, they can be indirectly affected if and only if a superposition in these degrees of freedom induces a superposition in space. For example, take a superposition in momentum. So a wave function which is localized, but in a superposition of two different momenta. Then after some time, the superposition in momentum turns into a superposition in position. And the superposition in position is localized by the object, and therefore the collapse in position induces indirectly a collapse in localization also in momentum. But if this doesn't happen, if the superposition in the new degrees of freedom doesn't turn into a superposition in position, these superpositions are left unchanged by the collapse mechanism. So typically superposition in spin are not affected by the collapse process. Okay, so I hope I conveyed a general picture of how these models work. I want to just to present a slide with the title, The Collapse in the Head, which wants to approach the main content of this workshop. So what happens? What is is there a possible relation between collapse in mind, collapse in consciousness? Of course, Penrose and collaborators suggested something along this line. This is a very difficult question. I will not enter into detail in this question, because consciousness itself is a delicate subject. So if you want to put even the collapse on top of that, it will become even more complicated. I want just to say something that has been discussed theoretically so far. And in particular, what happens to the perceptive process in the human eye, it could be also smell or whatever, something in the ear, whatever. So the visual process is more, at least psychologically, more effective. So suppose that you send to the eye a superposition of a photon going to the, for example, to the left eye, or a limited number. A photon is not sufficient probably, but a very limited number of photons, 5, 6, I think that's the threshold of vision, about 10 or less photons, that you send in a superposition of going to the left eye or to the right eye of a person. Now, the question is, so this is a microscopic superposition. It's even superposition of photons. Photons are basically not affected by collapse models. They remain in superposition for as long as you want. So what happens to this superposition when it hits the eye, the retina, and then it generates the electric signal which goes into the brain? So again, this is a very difficult question because the visual process from the microscopic point of view is a very complicated system. The motion of all the ions and molecules, it's not easy to trigger. It's a stochastic process even, it's not deterministic, of course. But you can say something, and some work has been done, and here you have some references over there. And basically, it's a very fascinating problem for the mathematical point of view because you have the formation, so the formation of the progressive formation of a macroscopic superposition. And I mean with that typically in a measurement process, you have micro and macro. The micro system in the superposition triggers the superposition of the macroscopic object, and then something happens to the object. Here instead, you have the progressive generation of the macroscopic superpositions. Over time, more and more atoms are included into the superposition during the perceptive process and during the building of the electric signal that goes into the brain. So on the one side, you have this micro to macro generation of a superposition. On top of that, you have the collapse of the wave function. So which of the two wins? How does it go over time? So again, this is a difficult question if you want to really study what happens in the eye. And so what has been done simply is to, so far, is to see at which point the number of particles or ions, let's say, that are included in the superposition is large enough in order to sharply kill the superposition. And then the answer, so basically at which stage of the perceptive process does the collapse become strong enough? And then depends on the value of the collapse parameter. If you remember, there is lambda and RC in the CSL model. This has been studied for the CSL model. And in particular, suppose that we fix RC. So the question is, how does the collapse during the visual process depend on lambda? And basically, there are two possibilities. If you take a strong value for lambda, we'll tell you later about these numerical values, suggested by Adler, then you can see that the collapse of the wave function becomes effective when the the photons hit the retina and start triggering the visual process. So basically where you have seen something, not in the brain, but in the eye. The eye reacts to the visual process. So at that stage, you already have a large enough number of ions included into the chemical process and into the superposition chemical process in the left eye plus chemical process in the right eye, that everything collapses and you have a classical signal, a classical outcome, which is brought to the brain through the optical nerve, and that's a classical signal with the classical visual perception and then the classical reaction of the brain to that perception. I've seen something with the right eye, with the left eye, or I've seen something with the right eye. Instead, if you take the GRW value which is a weaker value, some 8-9 orders of magnitude weaker value for the collapse strength, then the quantum to classical transition doesn't occur in the eye. It occurs much later. So the reaction of the eye is still quantum, superposition of a chemical reaction in the left and superposition of the chemical reaction in the right. Then you have the electric signal that goes through the optical nerve to the brain, and you have a superposition of a signal generated in one optical nerve and the signal generated in the other optical nerve. And basically, when you are more or less at the end, when the optical nerve merges with the brain, that you have a classical, the quantum classical transition. So at the end, I mean, for the typical values of collapse models, you can guarantee that you have a classical perception and then a classical reaction of the brain. And that's why basically we see a classical world that we behave like classical people. So this is not really the answer to the emergence of consciousness or whatever, but it's something, a more physical question, a much easier question to answer when a quantum signal becomes a classical signal. The question, the more detailed question of analyzing this problem dynamically, so to take the collapse and the formation of the superposition really together as a dynamical, as two competing processes within the same dynamics, is still an open question. Actually, it's part of an FQI project that we also that we won, which is, I think, at the same time where the project, which is the trigger of this workshop, has been granted. Okay, so this is what I can say about the collapse and the visual process, the collapse in the head. Okay, so why should the wave function collapse? That's also an interesting question. Collapse models do not tell why, they tell how, but not why. And why is another difficult question. There is no unique answer, not clear answer. According to GRW, the original proponents of collapse models, this is, and also Philip Pearl, I would say, the answer was, I think, is it's nature. Nature is such that the fundamental equations are nonlinear and stochastic. They're not linear. They are nonlinear. So it's a property of nature. But I think that still the origin of the question of why the wave function collapses calls for a physical answer. And one answer has been given by Penrose, and who relates the collapse of the wave function to gravity. And his argument, more or less, is the following one. When you have a superposition space, we're talking always of a matter superposition, of massive superposition space. If you inject into this description a little bit of quantum gravity, then the superposition in space, of mass in space, generates a superposition of two different space-times. A bump here, if the mass is located here, and plus a bump there in space-time if where the other component of the superposition is located. And then he says that the correct quantum theory of gravity should not allow for such superpositions of space-time. So the problem is not with the superposition of matter. The problem is for him is with the superposition of different space-time. For him, this is not a stable state of a quantum theory of gravity. It is a state that should localize over time. And then he gives some mathematical arguments as to why he thinks this is the case. And then if the superposition of space-time collapses into one of the two possibilities, then it brings also matter. The collapse of the system with it. So the space-time collapses, and also the matter field collapses and becomes localized in space. So this is the general idea. Of course, making a theory out of this would be the holy grail of most people. It's a very difficult question, but Penrose was succeeding in giving an estimate of the times, at least of the time scale at which the collapse should occur. And the estimate is in this picture made by Penrose himself. So the time, the lifetime of a massive superposition should be given by h bar over some energy. So this is the usual Heisenberg relation. So where the energy is computed as the gravitational content of the superposition. So in the normal, I mean, it could be in the general relativistic setting, but it's much more easier to compute in the Newtonian. So you can well imagine that if you have a proton here plus a proton there, the gravitational content is very weak, and so nothing happens. But if you have the Schrödinger cat here plus the Schrödinger cat there, the gravitational content is much larger, and something could happen. And actually, if you plug in the numbers, you can see that the lifetime of the superposition of a proton is very large, and the lifetime of the superposition of the Schrödinger cat is very short. So again, a quantum to classical transition. Sorry, but okay. Now I want to come to the testability of these models. These models are experimentally testable because the Schrödinger equation is modified. It's modified by adding additional terms, additional effects that you can try to test these effects. And there are two strategies which can be employed: interferometric and non-interferometric experiments. So interferometric experiments is basically the double slit experiment, as I showed in the picture. So the idea is that you take a system which is as large as possible, as massive as possible. You create a superposition. You keep the superposition for as long as possible in a protected environment, so no decoherence, and then you do the double slit experiment. If you see an interference pattern, that means that the superposition lived for all the time, and then collapse models are wrong because collapse models predicted that the superposition should not survive. Or if you see that, or if you do not see an interference pattern, then something happened. And the question is, what happened there? Then we have to investigate whether collapse models are right, or something went wrong with the experiment, or there was an unknown degree of freedom which was not taken into account, whatever, something happened. The other possibility is to perform non-interferometric experiments. Non-interferometric experiments are based, basically, I hope that the picture conveys the message. Are based on the indirect effect of the collapse mechanism. That every time you collapse the wave function, you also move the center of mass. So if there is a collapse mechanism, there is also a diffusion process. So the picture gives an idea, but one should look at the equation in the end. So if you take a superposition, the center of mass is located in the middle, so the mean position. But if you collapse to one of the two possibilities, the center of mass moves to the left or to the right in the picture. So the collapse, so this is just a pictorial way of representing a mathematical fact that a collapse dynamics induces a diffusion of the particle. According to standard quantum mechanics, the particle should go straight if there is no other force, of course. According to collapse models, it will jiggle because there is this noise, the collapse noise that disturbs the dynamics, which is omnipresent. It's always there. You cannot isolate it. So what are the advantages or disadvantages of the two approaches? The advantages of interferometric experiments is that they are a direct test of the superposition principles. You can even forget about collapse models. You are testing whether superpositions are there or not. So this is very important. But there is also a minus side. They are very difficult to perform. So it's very difficult to take a large system, keep it isolated, prepare a superposition, maintain the superposition, and detect the superposition. It's extremely difficult to do that. And in fact, at the moment, the world record for a delocalized state was achieved with some molecules weighing 10 to the 5 atomic mass unit. So a molecule with 10 to the 5, 10,000 nucleons. So about, roughly speaking, 1,000 atoms, which was a success from the experimental point of view. It's very difficult to perform such experiments, but it's still, you're not probing the macroscopic domain. You're still in the low mesoscopic world. Or the largest delocalization, about 0.5 meter, was achieved in a lab, but with single atoms. So it's a macroscopic delocalization, but for a microscopic system. So non-interferometric experiments instead are the opposite. So the minus side is that they are not a direct test of the superposition principle. They are a direct test of collapse models. They are, but not of the superposition principle per se. And but they are much easier to perform. Sorry that you have the small baby that is. Apologies. Just a second. I hope you can still hear me. Okay, sorry. But the downside is that you have to pay a price. You're not testing directly quantum superposition, but you're testing collapse models. The plus side is that they're much easier to perform because this noise is there all the time, even if you do not have a superposition. So if you have a superposition, the noise collapses the superposition. But if you do not have the superposition, the noise still induces a diffusion on the system. So you do not need to prepare a superposition to test the noise and to test collapse model. And in fact, they are much more effective in testing, non-interferometric experiments are more effective in testing this. So there are three strategies that have been employed with non-interferometric experiments. So one is to apply to cold atoms. So you take a cloud of cold atoms, you make it very cold. So basically the cloud shouldn't move. But if there is the collapse noise there acting on the cloud should expand a bit. Then you see whether the cloud expands or not. If it doesn't expand, nothing happens. If it doesn't expand, the collapse models are wrong. If it expands, again, let's see why. Or you take charged particles. If you have a diffusion is an acceleration diffusion. So if the particle accelerates, a charged particle is radiation. But all particles in real life, electrons, protons, forget about neutrons, are charged. So you should see some faint, very faint electromagnetic field coming out of matter because the matter is shaken by this noise. And Catalina probably will say much more about that in the talk. Or you can take a cantilever. Cantilever, it's basically an harmonic oscillator. And then if you cool the harmonic oscillator, it should more or less stabilize in the ground state. But if there is this noise, it will not stabilize in the ground state. It will still oscillate, and then you can check this oscillation and see what happens. Okay, so we use the second type of experiments. So the emission of radiation was used to test and actually rule out the Penrose model, at least in the easiest formulation. So you can still fix the model. So and again, I will say something quite much very quickly because perhaps Catalina will talk about this also later from the experimental point of view. So we did the theory part of the story. So in the Dioschi-Penrose model, if you remember, it collapses when the correlator is given by the Coulomb potential. The 1 over r shape. The 1 over r shape is always problematic because when you make integrals, they diverge. So if you have point-like particles, so you have to fix the problem by making particles extended over space, a little bit extended, not much. So you have a cutoff R0. So this model actually has a parameter, a free parameter that you want to test. If the smaller the parameter, the stronger the effect, the stronger the collapse. So if you make an experiment, you do not see anything, then you are putting a bound on this parameter, an upper bound, the lower bound, sorry. The parameter R0 cannot be too small because again, the smaller, the stronger the effect. So what is the size of R0? So what does the theory says about that? So you have to guess some number. Penrose and Dioschi suggested two things. So Penrose suggested that it should come, from a mathematical procedure which goes through the solution of the Schrödinger-Newton equation. I do not want to talk about that, but the moral is that each physical system has so to say, a natural value of R0. An isolated system, an isolated atom has a value of R0. An atom in a crystal has another value of R0. It's computed depending on the physical system. But there is a well-defined algorithm to compute it. Dioschi instead originally suggested that it has a defined value. So every particle has a defined value independently of whether it's isolated or in an atom or whatever. This original idea of Dioschi was later abandoned. Okay, so we try to test this model, again, to test the noise, to test the effect of the noise as emission of radiation. So we computed the photon emission. And here you have, in the box, you have the number of photons per unit frequency that should come out. And you see basically in the formula, I don't want to go too much into detail. You see basically that all the constants that should be in the game are there. So capital G, gravity, because it's a Dioschi-Penrose model, the electric charge, because we are talking about photons, for example, and then N and N sub A basically is a way to measure the number of protons. So it's the size of the system. So the larger the system, the more photons should come out. As you see that you see R0 in the denominator, again, the story I told you before, the smaller R0, the stronger the effect, so the more photons should come out, and then the rest I do not want to talk about. The technicalities not relevant for the present talk. Okay, so there is a theoretical prediction to first order in perturbation theory within a certain range of validity and so on and so forth. And okay, so I'm going to speak about the experiment because I'm not the best qualified person to talk about it. It's a technically challenging experiment with the germanium crystal in the Gran Sasso laboratories in Italy. So from right to left, you have a picture from above the laboratories, a picture inside.
the laboratories and the schematic of the germanium experiment. Here you have the experimental data, which have been analyzed by the experimentalists from the group of Catalina. And then this is the outcome. The outcome here, you see the lower bound. So the green bar tells you that all values of R0 up to some number between 10 to the minus 11, 10 to the minus 10 meters is excluded by the experiment. R0 cannot take that value. The point is that if you apply the prescription of Penrose to the germanium crystal, R0 should be below 10 to the minus 11 meters. So that value is excluded. So the original idea, so the moral is that the original idea of Penrose implemented in the DP model is ruled out experimentally. Again, I don't want to speak about natural ways out from the problem, but you have to make the model richer than the model that was presented so far. So what about the CSL model? The CSL model, the story is more difficult because there is a wider range of possibilities for the collapse. So there are two parameters first, RC and lambda, and there is not much is known about that. GRW and Adler suggested two completely different values for lambda, which are some 8-9 orders of magnitude separated from each other, and basically, and they are the black points in this exclusion plot. And then, so the gray area is a range of value which is excluded by the requirement that these models are effective at the macroscopic level. So if you require macroscopic objects to be localized, then the values cannot be too weak. And then the green area is basically these weak values which make the models useless. And then the question is how to bound from above, or hopefully one day to see something. So far, no one has seen anything so far. And so you can only exclude values of the parameters. This is the state of the art, and I'm going towards conclusion, I think. Yes, with the interferometric experiments. So experiments with atoms, experiments with molecules, experiments with crystals, and all the colored regions are values of the parameters which are excluded because the experiments proved, verified the quantum superposition principle. You see that the white area, which is the unexplored area, includes a large number of orders of magnitude of parameters. With non-interferometric experiments, instead the situation is much better, as I mentioned before. So with cold atoms, all the orange area is gone. With again a photon emission, with spontaneous photon emission, the purple area is gone. With optomechanical systems, so here is a gravitational wave detectors, so large optomechanical systems, the right area is gone. And with mesoscopic optomechanical system with cantilevers, the middle area is gone. And then with several updates. So this is the state of the art about testing collapse models. You see that, I mean, much have been excluded, but now the game becomes interesting because now you have a finite region which you want to focus and to see whether really there is a collapse of the wave function as predicted by the CSL model, or whether the model basically is ruled out and one has to seek for an alternative. Okay, so I'm at the end of my talk, so I want to thank my group and the funding agency. And thank you for the attention.